The Japanese aircraft bursts into flames without any warning whatsoever. Within a fraction of a second, what had been a sleek combat plane slicing through tropical air at 300 miles each hour transforms into a blazing inferno plummeting toward the water below, dragging behind it a tail of dark fumes resembling a death banner. The American aviator scarcely has enough time to comprehend what just occurred. His finger had just lifted away from the trigger mechanism. Half a dozen streams of heavy-caliber projectiles had merged together perfectly. A brilliant white spark appeared, far brighter than standard tracer ammunition, distinctly different in character. Then suddenly the enemy warplane simply ceased to exist as a functional aircraft. The date is January 1943. The location is somewhere above the Solomon Island chain. The Wildcat aviator will make his way back safely to Henderson Field Airstrip, carrying film footage from his aircraft-mounted camera that will cause military intelligence analysts to lean in closer with intense interest and growing excitement. Frame by careful frame, these officers will examine the sequence repeatedly, studying every detail visible. The incendiary projectile penetrates the Zero's wing root area, creating a white-hot point of intense heat. Then comes the catastrophic explosion, as aviation gasoline ignites violently inside a completely unprotected storage container. This outcome is not the result of random chance or battlefield luck. This represents the practical application of chemistry combined with precise engineering principles. A genuine revolution in the conduct of aerial combat operations that transformed the Pacific Theater's most dreaded fighter aircraft into something that burned like dry kindling. But here is the remarkable truth that almost nobody understood during those desperate days, and what historical records have mostly overlooked in the decades since. The projectile that just destroyed that Japanese fighter had not originally been created with that specific aircraft in mind. The ammunition Allied forces were deploying, the rounds aviators referred to as silver-tipped death, had been invented during a frantic development effort thousands of miles distant from the Pacific battleground. British weapons developers, working in 1938, observing the skies growing darker across the European continent, had created something entirely new, something capable of generating fire from metal components. The Japanese Zero fighter entered operational service in 1940 as arguably the finest carrier-launched fighter aircraft anywhere in the world. Its range was exceptional, its turning ability was absolutely unmatched, and its combat success ratios in China reached 12 enemy aircraft destroyed for every single Zero lost. When Pearl Harbor shattered the peaceful morning of December 7, 1941, Zero aviators controlled the airspace with frightening levels of efficiency and skill. What Allied military intelligence did not immediately announce publicly, what required examination of captured aircraft, and comprehensive battlefield documentation to verify conclusively, was the Zero's critical weakness. No protective armor plating surrounded the pilot, no self-sealing fuel storage containers existed, just welded aluminum tanks filled with hundreds of gallons of high-octane aviation fuel wrapped in nothing except thin metal covering. The Japanese designers had made a calculated strategic trade, sacrificing protection entirely in exchange for superior performance characteristics, eliminating weight to gain additional range capability. This was a design decision that would ultimately cost them thousands of experienced pilots. And the entire situation came down to a single type of bullet that most people have never learnt about in history classes. England, 1938. The European continent is holding its collective breath in anxious anticipation. Adolf Hitler's Germany becomes increasingly aggressive and bold. Spain continues bleeding through brutal civil war. And inside the production facilities of Woolwich Arsenal, a Belgian inventor whose name is WWII is presenting something that functions imperfectly. His incendiary projectile appears elegant when examined theoretically, a compact round filled with chemical compounds that burst into flames upon striking the target. No external flame source required, no tracer element betraying the shooter's location, simply contact followed immediately by combustion. The significant problem is that it detonates inside weapon barrels prematurely. When British testing personnel fired WWII's ammunition through heated weapons, recreating the actual conditions of prolonged aerial combat situations, the rounds explode before leaving the barrel. Barrels swell outward, some rupture completely. The fundamental design shows brilliance, but contains fatal flaws for sustained aerial warfare. where machine guns discharge thousands of rounds continuously until the metal itself glows bright red from the heat. The Air Ministry finds itself running desperately short on available time. The old phosphorus incendiary projectiles left over from World War I have become completely obsolete and inadequate. They ignite upon firing, leaving a clearly visible smoke trail that makes fighter aircraft easy to track and target. Even worse, they maintain effectiveness only to approximately 350 yards distance, rendering them useless when engaging modern bomber aircraft at extended ranges. Enter Major C. Aubrey Dixon, a specialist. He works as a Ministry of Supply ammunition expert, operating from windowless rooms located at Woolwich Arsenal facilities. His assignment is simultaneously simple in concept and impossible in execution. Make DeWild's fundamental concept function properly before war erupts across Europe. Dixon begins from the absolute beginning. He retains DeWild's core idea, which is impact-activated incendiary composition, but redesigns absolutely everything else, including the chemical formulation, the physical geometry, and the ignition mechanism itself. His innovation involves a small steel sphere embedded within the bullet's tip section. Upon impact, this sphere functions as a striking element, compressing the incendiary composition forcefully against the hardened jacket. The chemical payload, called SR-365, a barium nitrate-based mixture, ignites instantly at 0.5 grams per individual round. By December 1939, Dixon's improved design receives official approval as the 303 Incendiary B Mark V designation. For operational security purposes, they continue calling it DeWild ammunition. Let the German forces believe the British are deploying the flawed Belgian design. Let them underestimate what is actually coming toward them in combat. The newly developed round proves twice as effective as previous incendiary ammunition types. One projectile in every 5 successfully ignites fuel storage tanks during controlled testing compared to only 1 in 10 for older ammunition designs. And critically important, it produces a clearly visible flash upon impact. Aviators can finally observe their shots connecting with targets. But across the Atlantic Ocean, American weapons engineers are observing these developments with intense professional interest. The United States maintains official neutrality. Unofficially, American ammunition manufacturing companies are reverse engineering everything the British provide them. The .50 caliber Browning M2 machine gun had been originally designed during World War I as an anti-aircraft weapon system. By 1940, it is being installed on American fighter aircraft in batteries containing 4, 6, or even 8 individual guns. The firepower potential is absolutely devastating, but only if the ammunition can deliver the promised results. American ordnance engineers studied Dixon's British 303 design with careful attention to every detail. They scale the concept upward significantly. A .50 caliber projectile is considerably larger, substantially heavier, and carries much more kinetic energy upon impact. The incendiary payload can be proportionally bigger. The final result becomes the M8 API, standing for Armor-Piercing Incendiary. It represents a masterpiece of compact, destructive capability. The projectile, weighing 647 grains, features a hardened steel core, providing penetration capability, topped with incendiary composition, marked with a silver tip for identification purposes. The chemical formulation is thermite-based, utilizing aluminum and magnesium powder that combusts at temperatures surpassing 4,000 degrees Fahrenheit. The M8 does not simply set fuel ablaze. It actively melts metal components while burning through them. Testing procedures are carried out at Aberdeen Proving Ground, located in Maryland. Engineers discharge thousands of projectiles into simulated fuel storage containers, constructed from welded aluminum, identical to the construction methods the Japanese utilize. The outcomes are remarkably consistent and genuinely terrifying in their implications. When an M8 penetrates an unprotected fuel storage tank, successful ignition occurs in 68% of documented cases. By late 1941, American fighter aircraft are being loaded with mixed ammunition belts, combining armor-piercing, incendiary, tracer, and standard ball ammunition in precisely calculated sequences. Typical Pacific combat loading arrangements become 1 tracer round, 1 armor-piercing round, 1 incendiary round, followed by 2 ball ammunition rounds. The tactical logic is absolutely devastating in its effectiveness. Armor-piercing projectiles punch clean through metal structures. Incendiary rounds ignite fuel supplies and ammunition stores. Tracer rounds allow aviators to observe their fire pattern onto targets. Ball ammunition inflicts structural damage throughout. A 3-second firing burst from a P-51 Mustang equipped with 6 guns places 90 individual rounds into the sky. Approximately 18 of those projectiles are incendiaries. Against a B-17 bomber equipped with armored fuel storage containers and redundant backup systems, these rounds prove useful, but not immediately decisive. Against a Japanese Zero fighter, however, intelligence analysts are about to discover the devastating effectiveness, because on December 7, 1941, everything changes permanently. Pearl Harbor burns intensely, the Philippines fall rapidly, Wake Island becomes overrun, and across the entire Pacific region, Zero fighters are achieving combat success ratios that make Allied military command physically nauseated with concern. Something must break in this deadly pattern. The Mitsubishi A6M0 is not merely good at its function, it represents a fundamental paradigm shift in what carrier-based fighter aircraft can possibly achieve. Designer Jiro Horikoshi had confronted an impossible requirement statement in 1937. Construct a fighter aircraft with the operational range of a bomber, the maneuverability characteristics of a biplane, and the firepower capacity to destroy modern aircraft, all from a single-engine carrier fighter weighing less than 2.5 tons. His engineering solution was radical weight reduction taken to extreme levels. Every single component underwent scrutinized examination. Horikoshi's engineering team developed extra super duralumin, an aluminum-zinc alloy exhibiting remarkable strength-to-weight ratio characteristics. They implemented flush riveting techniques to reduce aerodynamic drag. They incorporated an integral wing design where fuel storage tanks were constructed directly into the wing structure itself, completely eliminating separate tank weight. No armor plating surrounded the cockpit area, no protection existed for the engine components, and crucially important, no self-sealing fuel storage containers. Self-sealing storage tanks had become standard equipment on British and American fighter aircraft by 1940. The underlying technology was relatively simple in concept. Rubber layers installed inside the tank that expanded when exposed to gasoline, automatically sealing bullet holes. The significant problem was that those rubber layers were substantially thick, reaching up to 1 inch in certain designs. When Japanese engineers conducted testing of self-sealing tanks in the Nakajima Tenzan bomber aircraft, fuel capacity dropped by 30%. 30% reduction. For a naval force operating across the world's largest ocean, that capacity loss was completely unacceptable. Japanese strategic military doctrine demanded maximum range above all other considerations. Aircraft carriers would launch strike operations from extreme distances, 300, 400, even 500 miles from target locations. The Zero needed sufficient fuel to fly outbound, engage in combat, and fly back successfully. Therefore, Horikoshi made his calculated choice. The A6M20 entered operational service in 1940 with a combat operational radius exceeding 1,150 miles when equipped with drop tank. Its rate of climb was exceptional by contemporary standards. At low speeds, its maneuverability remained absolutely unmatched by any opponent. Any Allied aviator foolish enough to enter a turning dogfight engagement was effectively signing their own death warrant. Over China, Zero aviators achieved combat kill ratios of 12-1. At Pearl Harbor, they controlled the airspace with impunity and terrifying efficiency. Not a single Zero was lost in air-to-air combat during the entire attack. Throughout the first 6 months of the Pacific War, the Zero appeared practically invincible. But that welded aluminum fuel storage tank, the one carrying 130 gallons of aviation gasoline wrapped in covering you could dent with your boot heel, was counting down toward disaster. The question was never if it would become a critical liability. The question was simply when. June 1942, the Aleutian Islands. A Zero fighter crashes on Akutan Island, Alaska. The pilot, Tadayoshi Koga, attempts an emergency landing on what he believes is solid ground. It is actually marsh. The aircraft flips violently, breaks Koga's neck, and sinks nose first into the frozen tundra. What happens next fundamentally transforms the Pacific War. A US Navy patrol discovers the wreckage nearly intact. The extreme cold has preserved virtually everything. Within weeks, the Zero is recovered, transported to San Diego, and subjected to the most thorough technical analysis American engineers have ever conducted on an enemy aircraft. They measure absolutely everything: weight distribution patterns, control surface effectiveness, engine performance characteristics, fuel capacity, construction methods. And they locate the vulnerabilities. The large aileron surfaces that give the Zero incredible low-speed maneuverability become heavy and unresponsive above 230 miles per hour. The carburetor contains a design flaw that causes the engine to cut out completely in negative G maneuvers. The roll rate is substantially slower to the right than to the left due to propeller torque effects. But the most critical discovery is something Allied intelligence had suspected, but could not confirm until examining this intact specimen: complete absence of protection for fuel system components. The Zero carries fuel in 3 distinct locations: 2 wing tanks holding 94 gallons total, 1 fuselage tank positioned behind the pilot holding 38 gallons. With a 72-gallon drop tank, total capacity reaches 204 gallons. Every single gallon sits in plain welded aluminum construction. No rubber bladder liners, no self-sealing compounds, no fire suppression systems whatsoever. A single .50 caliber round penetrating any of these tanks produces one of 2 results: either a slow fuel leak or immediate catastrophic ignition, depending entirely on whether incendiary ammunition is involved. American test aviators develop new tactical approaches. Never engage in dogfighting. The Zero will outturn you every single time. Instead, utilize altitude advantage. Dive in fast. The Zero cannot roll quickly enough to evade. Fire a short, controlled burst. Climb away using superior power and diving speed. They call this tactic boom and zoom. The tactical information spreads rapidly through fighter squadrons. Marine Corps units at Guadalcanal receive detailed briefings. Navy aviators aboard carriers get the intelligence reports. But knowing the Zero's weakness and successfully exploiting it are entirely different things. You still must hit a fuel tank in actual combat at 300 miles per hour while the Zero is maneuvering, while its pilot is simultaneously trying to kill you. That is where the incendiary round makes all the difference in survival. Guadalcanal, August 1942. Captain Marion Carl of VMF 223 is already an ace. Midway veteran, 3 confirmed kills. He flies a Grumman F-4F Wildcat, a stubby, rugged fighter that the Zero can fly circles around. Literally, the Wildcat is slower, less maneuverable. Its climb rate is inferior. On paper specifications, it should not survive against Zeros. But the Wildcat has something the Zero does not possess: protection. Self-sealing fuel storage tanks, armor plating behind the pilot's seat, rugged construction that can absorb battle damage and continue flying, and 6.50 caliber Browning machine guns loaded with that new mixed ammunition. Carl's squadron receives intelligence briefings on Zero vulnerabilities. They are told about the Akutan Zero findings. Avoid turning engagements. Use diving attacks. Aim for the wing routes. That is where the fuel tanks are located. And they are told about the incendiary ammunition. When you see white flashes on impact, you know you are hitting them correctly. The intelligence officer explains, "Those are the incendiary rounds detonating. Keep firing into those flashes. The Zero will burn." On August 24th, 1942, the test comes. A formation of Japanese bombers approaches Henderson Field, escorted by Zeros. VMF 223 scrambles. Carl leads his division into altitude, positioning above and behind the enemy formation, then dives. The Wildcat accelerates in the dive, building speed the Zero cannot match. Carl selects a Zero flying escort. His gun sight settles on the enemy fighter's wing route. His thumb presses the firing button. 6 streams of .50 caliber converge. Tracer rounds arc toward the target, and then the white flashes start appearing. Incendiary rounds striking metal. Some penetrate the wing skin. One finds the fuel tank. The Zero's wing erupts violently. Not a small fire, not gradual combustion spreading slowly. Explosive ignition of aviation fuel in an unprotected storage container. The wing structure, lightweight aluminium designed for minimum weight, offers absolutely no resistance to the spreading fire. Flames spread through the internal structure at impossible speed. The Zero breaks apart in mid-air. Carl pulls out of his dive, already searching for his next target. Behind him, burning debris tumbles toward the jungle below. In his gun camera footage, grainy black and white film that will be analyzed frame by frame, you can see it clearly. The moment of ignition, the flash, the catastrophic failure. The incendiary round has just done exactly what it was designed to do, and this is only the beginning of a pattern that will repeat thousands of times. But let us step into the cockpit of a Zero pilot experiencing this new threat. Flight Petty Officer Saburo Sakai is one of Japan's greatest aces. Over 60 confirmed kills, legendary marksmanship skills. Survivor of dozens of dogfight engagements. On August 7, 1942, he flies escort over Guadalcanal when he spots them. American dive bombers returning from a strike mission. Easy targets, he believes. He attacks. What Sakai does not see is the Wildcat division positioning above him. The first burst hits his Zero from behind and above. Classic boom and zoom attack. Rounds punch through the thin aluminium fuselage. Some are armor-piercing, passing completely through. Some are ball ammunition, tumbling after impact, tearing irregular holes. And one is incendiary. It strikes the fuselage tank. The flash is blinding even through the aluminum skin. Gasoline vapor ignites instantly. Flames shoot through the cockpit. Sakai's face is burning. His goggles have melted. He cannot see out of his right eye. It has been destroyed by bullet fragments. Aviation fuel is on fire behind his seat. The Zero is one of history's most maneuverable fighters. But right now, Sakai does not care about maneuverability. He needs to escape the burning cockpit before he cooks alive. He cannot bail out. He is over enemy territory. Death or capture await below. So he does something extraordinary. He flies home. Nearly blind, face scorched, cockpit filling with smoke from burning fuel and melting components. The 4-hour flight back to Rabaul becomes a test of pure will. He makes it successfully. Lands with the Zero's tail section partially burned away. The ground crew is horrified when they pull him from the cockpit. Sakai will survive. He will even return to combat operations, flying with one eye for the rest of the war. But his Zero is a total loss. Not from structural damage, the American bullets had mostly passed through cleanly, but from fire damage. The incendiary round that ignited his fuel tank had done more damage than a dozen armor-piercing rounds could have achieved. This pattern repeats across the Pacific Theater continuously. Zeros absorbing multiple hits from ball and armor-piercing ammunition, flying home damaged but intact. Zeros taking a single incendiary round in a fuel tank, burning to nothing in seconds. The mathematics of aerial combat are changing fundamentally, and Japanese pilots are starting to understand what it means for their survival. The psychological impact is immediate and devastating. Zero pilots had entered the war believing in their aircraft's supremacy. 6 months of victories reinforced that belief system. The Zero could outfly anything, outmaneuver anything. The code of Bushido taught that skill and spirit could overcome material disadvantage. But fire does not care about Bushido. Fire does not care that you are a veteran pilot with 20 kills. Fire does not care that your Zero can turn inside any other fighter in the world. When incendiary rounds find your unprotected fuel tank, you have maybe 3 seconds before the wing separates completely. Japanese war diaries, the ones that survived the conflict, record this shift in understanding. American ammunition now causes immediate fire. Most losses are from burning, not battle damage. That comes from a unit report in late 1942. Pilots fear the incendiary rounds more than accurate shooting. A single hit can destroy the aircraft. That comes from a flight leader's after-action report. The fear becomes specific and rational. When you know that any hit to your fuel system might be your last, the calculation changes dramatically. The aggressive tactics that worked over China, closing to point-blank range, extended dogfights, pursuing damaged enemies, become suicide. Because American fighters are now loaded with mixed ammunition, every belt includes incendiaries. You cannot see which rounds are which until they hit. A stream of tracer fire might include 5 or 6 incendiary rounds. You will not know which ones until the white flash appears, and by then, it is too late. Now, let us examine the technical specifications that made this possible. The M8 API round is deceptively simple in appearance. Total length 5.45 inches. Total weight 647 grains, about 1.5 ounces. Silver painted tip for identification. Inside that simple exterior is precision engineering. The projectile consists of 3 main components. First, a hardened steel penetrator core weighing approximately 355 grains. This provides the armor-piercing capability. Though against aircraft, armor piercing is relative. The Zero has no armor whatsoever, so the penetrator simply ensures the round punches through aluminium skin without deflecting. Second, the incendiary composition. Approximately 15 grains of IM-11, a thermite-based mixture. That is about 1 gram of material. Does not sound like much, but thermite reactions are exothermic. They generate their own oxygen and burn at temperatures that melt steel. Third, the mechanical fuse. A small steel ball or crushing element at the bullet's tip. On impact, this compresses the incendiary composition against the penetrator core, initiating the thermite reaction through friction and pressure. The sequence happens in milliseconds. Impact occurs. The steel ball crushes the incendiary composition. Chemical ignition occurs. Aluminum powder reacting with iron oxide and other oxidizers. Temperature spikes above 4,000 degrees Fahrenheit. The thermite burns through the bullet jacket, spraying white-hot particles into whatever space the penetrator has just created. If that space is a fuel tank filled with aviation gasoline vapor, ignition is nearly instantaneous. February 1943, the Solomon Islands. Lieutenant Jefferson de Blanc of VMF 112 is escorting dive bombers on a strike mission. His F-4F Wildcat carries the standard load, 1,200 rounds total, across 6 guns, mixed ammunition in each belt. The strike goes well, bombs hit the target, but on the return flight, de Blanc's external wing tanks malfunction. He is burning fuel fast, working off his internal tank only. The sun is setting, and then he sees them. 5 Japanese aircraft inbound toward the vulnerable dive bombers. De Blanc does not hesitate. He is outnumbered 5 to 1, low on fuel, and the sun is dying. But those are his bombers, his mission. He attacks. The first Japanese float plane comes apart in his gun sight. Incendiary rounds walk across the fuselage. Fire blooms. The aircraft tumbles into the ocean. The second float plane tries to evade. De Blanc follows, firing in short bursts to conserve ammunition. More white flashes, more fire. Another enemy down. Then the Zeros arrive. 3 A-6M fighters, faster and more maneuverable than anything de Blanc is flying. They split up trying to get on his tail. De Blanc uses every trick, vertical maneuvers, using the Wildcat's superior diving speed, never staying in one flight path long enough to be an easy target. His guns find 1, 0. The incendiary rounds do their work. Wing tank ignites. The fighter breaks apart. De Blanc manages to crash land in the ocean near a coast watcher station. Natives rescue him. Weeks later, he makes it back to Allied lines. His mission report lists 5 enemy aircraft destroyed in one engagement. The gun camera footage confirms it, frame after frame showing the same pattern. White flashes of incendiary impact, then catastrophic fire. By late 1943, the pattern is undeniable. American fighter squadrons across the Pacific are achieving kill ratios that would have seemed impossible 18 months earlier. The F-6F Hellcat, specifically designed to counter the Zero, is entering service with even heavier armament. 6.5 caliber guns with 400 rounds per gun. That is 2,400 rounds total. About 480 of them are incendiaries. But the ammunition has not changed. Still the M8 API. Still the same thermite composition. Still finding those unprotected fuel tanks. Japanese losses are becoming unsustainable. At the Battle of the Philippine Sea in June 1944, the Great Marianas Turkey Shoot, American fighters downed 243 Japanese carrier aircraft against only 23 American losses. The primary cause of Japanese losses is aircraft fires following incendiary hits. So why did not Japan adapt? The answer is complex, involving engineering, economics, and culture. First, the engineering challenge. Japan's industrial capacity was a fraction of America's. While US factories were producing millions of rounds monthly by 1943, Japanese ammunition production struggled to meet basic demand. Developing a new incendiary round would require chemical research, testing, production, retooling, and quality control. Resources Japan increasingly did not have as the war ground on. Second, the strategic miscalculation. Japanese naval doctrine had emphasized the decisive fleet battle, one massive engagement that would destroy enemy carrier forces and win the war. The Zero was designed for that single crucial battle. The idea of a prolonged attrition war across thousands of miles of ocean, the actual war they got, was not part of the planning. Third, the cultural factor. Japanese military culture emphasized spiritual strength and pilot skill over technological superiority. The aftermath is measured in numbers that do not quite capture the human cost. Of approximately 11,000 Zeros produced during the war, the majority were lost to combat or operational causes. American records suggest that incendiary ammunition played a role in destroying roughly 40 to 50% of Zeros engaged in aerial combat. That is thousands of aircraft, thousands of pilots. After the war, the Strategic Bombing Survey interviewed surviving Japanese officers and engineers. Their assessment was blunt. The decision to prioritize range over protection had been rational given 1930 strategic assumptions, but had proven catastrophic in practice. Today, the M8 API round is largely forgotten outside military history circles. Museums display restored Zeros with polished paint and pristine canopies. The aircraft looks elegant, dangerous, revolutionary. What you do not see in the museum display is the vulnerability, the welded aluminum fuel tanks, the absence of protection, the engineering trade-offs that made sense in 1940 and became death sentences by 1943. The British 303, Incendiary Mark V, and the American M8 API were never glamorous weapons. They did not win headlines. There are no monuments to incendiary ammunition, but their effect on the Pacific Air War was profound. They turned the Zero's greatest design choice, weight reduction for range and maneuverability, into its fatal flaw. The Zero and the incendiary round are locked in history together. The revolutionary fighter and the forgotten bullet. One represented the peak of 1930s aircraft design philosophy. The other represented a new kind of warfare, chemistry and engineering defeating spirit and skill. Perhaps we should also remember a silver-tipped bullet, traveling at nearly 3,000 feet per second, carrying 1 gram of thermite. The round that turned Zeros into falling stars.